Now it's time to develop a better method than the rectangle methods, and I will actually do it 3 times for the price of 1, which is a wonderful deal. But I will actually start with the rectangle methods. Let's have a look at them. In the last panel, we can see that the left rectangle method is actually undershooting, while the right rectangle method is overshooting the mark. On the other hand, when we look to the left, to the second panel from the right, it's the same story, they just reverse their positions. Right rectangles, they undershoot, left rectangles overshoot. So whenever the function is monotone, these 2 rectangle methods are actually bracketing the correct answer. And as we know, every reasonable function can be split into intervals of monotonicity. So this is actually fairly typical. I have 2 methods, none of them as itself is exactly great, but they do bracket the correct answer. Why don't I take the average? This looks like an interesting idea. So here is an idea. What is the average? How do you take average? You sum up and then you divide by half. So we divide by half and then we sum up. When we are summing up, again, we can factor out this step size h and what is left. So I'm summing up and the leftmost value is taken just once because only one of the methods really cares about it. But then the next value, x1, is actually used by both methods, the left and the right rectangles. So it's taken twice in the summation. And this is actually true for all the others, almost all the others. We go to the one which is next to the last one, xn minus 1, which also appears here in the summation. And the last value is taken just once. Okay, here we go. So that's the average of these 2 rectangle formulas, and I think, naively, that it approximates well my integral, hopefully. So that was the first derivation, taking average of upper and lower estimate. Looks like an interesting idea. Let's have a look at another derivation, and we start with a panel. Here is a panel. Let's imagine a function. I'm taking left rectangles, I'm taking right rectangles, and I'm taking the average for this one panel. How does the average look like? Well, it's 1/2 of h of f at the left endpoint, and I think it will be easier a little bit if I put again c and c plus h. So it's f at c plus f, c plus h. So what I did here globally, this averaging of 2 formulas, I did here on the level of just one panel. Let's rewrite it. This is h times fc plus h divided by 2. So what I was really doing is this. I can see product of 2 values, and one of them is actually the base of my rectangle. So this formula can be interpreted as an area of some rectangle which has base h, and the height is the average of height on the left and on the right. This sounds interesting. You have 2 candidates, one candidate, another candidate, and you do not know which one to take, so you split the difference, you get the average. I'm actually not taking this as a second derivation. Rather, I take it as a different point of view at this averaging business. But this is actually very hopeful because when I use the average, what happens to the error? Well, sometimes I'm overshooting and sometimes I'm undershooting. So one of these errors is positive, one of them is negative, and they will cancel to some extent. Perhaps not entirely, I shouldn't be too optimistic, but they will cancel to some extent. So I expect this is much better than the previous attempt that we did over here. So that's another justification, but this is still the averaging business. The real trick comes now. I look at this formula and I start thinking back to elementary school. Did I see such a formula before? Let's forget about averaging. Let's really see it as a whole. Did I see something like that before? And the answer is yes. There is a formula about area, which is exactly like that. And that's the area of a trapezoid. When I was at elementary school, they have shown me a picture like that, where h was the height of the trapezoid, fc was one base, and fc plus h was the other base. So I can also interpret this expression, this summation over one panel, as the area of a trapezoid. This is how I was used to see it at elementary school, but let's rotate it. When we rotate it, it looks like this. Here is my panel, C plus H. The width is H. I have two values that I'm interested in. These are my data. There is function passing through. And I'm actually, instead of integrating, calculating the area of a trapezoid. So I'm connecting these two with a straight line and taking this as my approximation. And I'm doing this in a specific panel. I look at it and I say, what is the error? And the answer is, the error is really tiny. Much better compared to rectangles. So this is wonderful. And this is actually the starting point for our second derivation of the new method. And I will start from the scratch. Let's forget about it. We have our familiar picture. Interval from A to B, our wave function, let's call it f. Equidistant partition, some panels over here. And our data, which is over here, 5 pieces of data. Now for the rectangle method, we used step function for our approximation, which means we used on each panel a polynomial of degree 0, a constant function. Natural question is, why don't I try polynomials of degree 1, which means straight lines? Looks much better. Over here, that's a nice approximation by a straight line. And also here, and here, and here. That's a good idea. Or another point of view, instead of rectangles, why don't I use trapezoids? Also a very good idea. Seems much better compared to rectangles. So let's develop our new method, our new inspiration, trapezoids. Here we have the step size. How do I approximate the integral? Well, I have to take the area of the first trapezoid. And again, mentally, I sort of imagine it like that. So it's the height. And now I have to take the average of the bases, which is now the left and right height in this trapezoid. So it will be the average of the value here, fx0, plus fx1. Then we add the second trapezoid. And the second trapezoid is using the value on the left and on the right. So fx1 plus fx2. And we keep going. Now, what do we do next? We factor out 1/2. Done. We factor out h. Done. What is left? fx0 here just once, because it's used only by one trapezoid. fx1 is used twice, because it serves two masters, so to speak. It's twice, and so on. Each value is used by two trapezoids, apart from the last one. This one is used just once. It all fits nicely. So this method can be also thought of as a natural generalization, passing from rectangles to trapezoids in the picture. This is the trapezoid method. And if I click, I sincerely hope it will be there. I recall myself typing it. Here we go. So on the right, we see the familiar formula, all values taken twice apart from the endpoints. And 1/2 and h. Great. Let's try it out. Example. Again, on a test, you may be asked to show approximation of a specific integral using trapezoid method. Partition size, let's say 4 per picture. We have seen this before, so let me, oops. Our example was going all the way up to 9. Of course, it's possible to do it all the way up to 2, but I don't feel like playing with fractions right now, so I will be nice on myself. Okay, so we have this partition. The step size was 2, and we find the approximation as follows. 1/2 h is 2, and then we are summing up the values. The first value is taken just once, logarithm at 1, twice the second value, which is 1 plus 2 is 3, plus twice the next value, 3 plus 2 is 5, plus twice the next value, 5 plus 2 is 7, And the last value is 9. 7 plus 2 is 9. Yeah, that fits. And as you can see, we are done. Again, on a test, perfect answer like that, I can see what you did. And on the test, you can be also expected to provide explanation for the trapezoid rule, which means explanation. I actually prefer sort of to see this picture with explanation of the area of a trapezoid and how it all comes together. Okay, you should be able to justify the formula, show where does it come from. Okay, so that's the trapezoid method. Very nice. Well, let's have a look at Maple. So I go back to our nice example. Let me go back to partition size 4 and change the method to trapezoid. And perhaps the output could be graph. Of course, we know what the picture will be, but it's nice to see it. Yeah, you can see the trapezoids, and they are much, much better at following the shape of the curve. Wonderful. Total error. That's what we are really interested in now. Here we go. Total error is 0.013. That's a nice number. My favorite is 13, so this is a good sign. Trapezoid method. You can see from the chart that there will be one more method. Anyway, you can see that the error is better compared to the left rectangle point. So it seems that our pictures and our intuition were right. But of course, we would like to see some mathematics. So now we have to erase, make a lot of room, and start thorough analysis of the error of the method for the trapezoid rule. Let's go for it. This will actually be a third independent derivation of our method. We forget about trapezoid rule. We never saw it before. We are just focusing on one panel. Here we have a panel, and we want to approximate in the best possible way the integral of our f over this panel. What kind of data do we have? That's a key question. Well, we know fc plus h, and we know fc. So using these two pieces of data, we want to match this integral as best as possible. Now, with the left rectangles, we decided to use fc. With the right rectangles, we decided to use fc plus h. But you can see the problem. Why use just one piece of data if you have two? Of course, we were wasting our information. So, what is the best way to somehow fit these two guys with this integral? And we don't know, because this integral and those values are of different kind. So, we have to pass two expansions so that we can match behavior. Let's write down expansion for fc plus h, again, when h is really close to 0. So the expansion is fc plus f prime ch plus 1/2 f double prime ch square plus, let me put oh cubed here. Okay, now we have a chance to match, because they are similar in nature. How about fc? Well, it's a constant function. The expansion of a constant function is a constant function. So we have three expansions, and using these two, we would like to find the best possible match for this expansion. So we're essentially comparing polynomials. And obviously, you have a problem here, but we can fix it if we multiply these two rows by h. So I just imagine that I multiply them by h. And you can see that those formulas are now getting much better together. They fit much better together because, for instance, here we can see f prime ch square, f prime ch square. They are much more similar. Wonderful. So how do we put them together in the best possible way? There is an interesting paradox in life that if you have too much freedom, it may actually restrict your imagination, your actual inspiration that you have. Because when you have too much freedom, you don't really know where to start. And if you get some restrictions, it focuses your energy in a certain direction, sometimes against those restrictions, but still you start getting inspiration. So here, if I just ask what expression will work best, there are infinitely many possible expressions. This is useless. This is pointless trying to do it that way. So I'm going to restrict myself to nice expressions because, after all, I don't want to calculate some beastly things with these pieces of data. And the most useful or most convenient expressions are linear combinations. So I will use a linear combination of these two pieces of data and obtain something which I will try to match as closely as possible to this target value. So this one will get multiplied by a constant, this one by a constant, and then I put them together. Okay? What do I get? Remember, I'm also multiplying by h. So, over here I get a times h fc plus h plus b h fc is equal to. They get multiplied by h, this one by a, this one by b, and then I add them, so I can factor out. I can factor out h, I can factor out fc, and there will be a plus b left. And that's it for this line. So everything just gets multiplied by a, by h, and copied. So it will be a f prime c h squared plus 1/2 a f double prime c h cubed plus constant doesn't change the nature of this O, big O expression, but I multiply it by h and raise all the powers. Here we go. So now I am trying to match these two expressions as well as I can, and we know that the most important term is the one with h, the lowest power. So let's start there. If I want to match these two expressions, then this guy has to be 1. And that's my first requirement. Okay, so do I have a right to arrange this? Yes, I have two parameters, I can do whatever I want. Great. The first term is matching. Let's pass to the second most important term, which is the quadratic one. I need, when I compare it, a to be 1/2. That's also an important requirement. And I have two parameters, two requirements, that's about it. That's the end of the road. So I see that the best match is obtained by taking a and b equal to 1/2. So what is the best approximation for the area under the function on this panel? And the answer is the best approximation is 1/2 h fc plus 1/2 h fc plus h, which is 1/2 h and summation, which is exactly the trapezoid rule. So we just confirmed that the trapezoid rule is actually the best use of information that we have in one panel, unless we want to do some crazy calculations. So the best reasonable use of information, which is wonderful. So this is the third derivation that the trapezoid rule should be good. Okay, now we know what we want to use for approximation, and let's find the error, so the local error. The local error, of course, is the actual integral minus the approximation. So the actual integral we can see over here, and the approximation we can see over here. So let me just mark it into it in some symbolic way. It's the integral minus, and let's call this one, let's say TH, the trapezoid approximation. And now what do we get? We are actually subtracting this series from this series, with the understanding that this is 1 and this is 1/2. So when we subtract, this term cancels, this term cancels, and this term we are not quite sure. So let's write it down. We are taking this and subtracting this, and I can factor out common parts. So there will be some subtraction which is left after I factor out, and I'm factoring out the second derivative of c and the cubic power of h. And from here we have 1/3 factorial, and from here we have 1/2 and also 1/2 for a. So we are subtracting 1/4. Then we are subtracting OH4 minus, and notice here this is OH cubed, but we are multiplying by h, so we are subtracting OH4. And therefore, the local error is, and now it comes. Okay, let me think about it. 6, 4, common denominator is 12. I have to multiply this one by 2, this one by 3, so it's -1. So far, so good. second derivative at c, h cubed, plus, here is a tail represented by big O, and the dominant power is the fourth power, another tail, another polynomial. When I subtract them, this h to 4 may cancel or may not, I don't know, so I have to play it safe. It's quite possible that h to the power 4 is still the dominant term. Okay, that's it. That's the local error. And now we can do exactly the same calculation as we did for the rectangle method, which means we would look for the global error. We would write down the definition, split the integral into integrals over individual panels, factor out, estimate the second derivative by the maximal possible value, and then use triangle inequality to estimate that this is at most 1 over 12. Then there will be b minus a coming in the same way that it came before. Then there will be the maximal possible value of the second derivative. And then there will be h cubed, but divided by h squared, and some tail. So let me put it just like that. The tail would be OH cubed, which will be less important than h squared. So this is really the dominant part of the error. And again, let's ask whether this makes sense. So we already noticed before that the error should be directly proportional to the integrating range, its size, its length, which is okay. It should be somehow proportional to the step size, and we see that the proportion works with h squared. So this is a better method. It's a method of order 2. That's important. And finally, there is some information about the second derivative. Does it make sense? Let's have a look at it. Here we have a function. We try to approximate by trapezoid. Is it a good approximation? I would say moderately yes. Can I think of a really, really bad approximation by trapezoid? And the answer is yes, if the function looks like this. Then I have a big error. Now, how can I tell apart these two cases? And it's obvious that it's not about the steepness. If a function is very steep or little steep or shallow, flat, this approximation by trapezoid works really well for steep functions, flat functions, no problem. What is really harmful for this approximation is when the function is curving a lot. And this intensity of curving is exactly the second derivative, concavity of a function. Okay? So it really makes sense. Let's confirm it. So here is a theorem. Here is M2, which is a global bound for the second derivative. And here on the left, we have the absolute error of the trapezoid rule. And we can see a formula with partition size. We are not surprised. And then we see formula with step size for specific permissible step sizes. And it fits with the formula that we derived, which is always a good feeling. Okay, so this works well. And again, let's talk about some interpretation. So first of all, we can write that EH is OH squared. It's a method of order 2, very important, which means that in particular, if I use step size h, then with a bit of luck, this error will be proportional to h squared. What does it mean? It means that if I divide the step size by some constant a, now we have to be careful. H has to be a permissible step size, and then if I divide it by an integer, positive integer, then it again is a permissible step size. Then the error will be c times, and now the new step is h over a, and it's squared. So it means that 1 over a squared can be factored out, and we are getting 1 over a squared, the original error. So we are getting a new picture. A new picture looks like this. We have step size and corresponding error. When I divide the step size a times, then the error decreases a squared times. And that's the benefit of higher order methods. Faster improvement, better reaction to the changes that we make. By the way, one can also work it like that. The error, as dependent on the partition size, is proportional to 1 over n square. And then when you want a better measurement, it means you have to multiply the partition size by some constant a, which should be positive integer. And you can follow similar calculation. Instead of n, you put a times n and you factor out, and you get 1 over a square en. So this would be like this indirect proportion, but not with constant, but with constant square. Okay, so I could make a picture like that. N, a times n, and the error en changes into 1 over a square en. So that's another picture that's possible. Okay, let's play. I returned to my original calculation that when the partition size is 4, the error for the trapezoid method is 0.013 approximately. What happens if I double the partition size? According to the scheme, doubling partition size or dividing the step size by 2 means I have to divide the error by 2 square, which is 4 times. So that's my estimate. That's my guess what happens with the error in this little part of my chart. So I divide this by 4 and I get 0.003 and something. So that's my expectation. Let's see what the actual error is for partition size 8. 0.003. Yeah, exactly. See, it works nicely. Let me return to this picture when I've been comparing error against the step size. And I talked about some step sizes not being permissible. That's why the picture is so funny. But here I am changing the method from the right rectangles to trapezoids. And let's see the picture. Well, does it confirm that the error behaves like OH squared? The answer is not quite. Because, well, I can see this curving shape, definitely. But how do I know that it's h squared? It could be h cubed. Or it could be h to 1.1. I don't know. Nobody knows. But what we see quite well is that it's not linear. It's much better than linear. This is a very, let's say, hopeful picture. And we can also try another trick. This ratio between errors and step sizes can be checked. And I have a little code here. Let's have a look at it. So in this code, I'm going to calculate approximation of my integral for 3 times. With partition sizes 4, 8, and 16. So these are doubles, all the time doubles. I look at the errors, I store them, and then I look at the ratio of the 2 successive errors. So I look at the ratio of errors between 8 and 4, and then the ratio of errors between 16 and 8. And we will actually see this constant. Okay? So first I do it for the method of left rectangles, which is linear. So if I'm doubling the step, I should see doubling of the error. Let's see. Here we go. And we can see the 3 errors. One of them is 0.21, which is in our chart. Then another one is 0.10. And then there is a third one. And we can see the ratio of the 2 successive ones, and it's close to 2, exactly as expected. Now I change the method to trapezoid. Here we go. And again, we see the errors, 0.13, 0.03, exactly as in our chart. Third error, and the ratios are really close to 4. So this seems to work really well. And that's essentially it regarding the trapezoid method. It's a very nice method. Method of order 2 are quite okay in numerical analysis. But for the integration, people were greedy, actually. Let's face it. People are sometimes greedy, and they asked, is it possible to do something better? And that's our next topic. Okay, so here we have the familiar picture for the last time, I hope. And a new question, pieces of data. And I'm thinking, okay, can I do better than trapezoids? We started with rectangles, and we used polynomials of degree 0 to approximate our function on each panel. Then we improved to polynomials of degree 1, and we got trapezoids. Notice, when the degree of polynomial was 0, we've got error of order h. When the degree was 1, we've got error of order h squared. Natural question, why don't I use parabolas? polynomials of degree 2. When the degree is 2, I would expect the error to be of order h cubed. Shouldn't it work like that? Oh, well, of course it should, if mathematics makes any sense. So how about putting parabolas over here into the picture? There is a problem. When you have 2 points in a panel, there are infinitely many parabolas that fit through them. How do you find the right one? It's impossible to solve. Too much freedom. Here is a trick. If the partition size is even, I can split it into groups of 2. And each group of 2 panels, I will call it panel again. It's slight misuse of notation, but okay. This will now be a panel for me. 2 panels, 2 panel, double panel, whatever. I see 3 pieces of data, and through 3 points in the plane, there goes a unique parabola. There is a unique quadratic function which passes like that. Now, what I could do is this. I could split the whole integrating range into pairs of original panels, now into double panels. For each of them, using general data, determine the formula for this parabola that passes through, or this quadratic polynomial. And then instead of integrating f, I would integrate the parabola and get a number. And I would sum up those numbers. And I would get a formula which should approximate the integral. Why won't I do it? Because it's beastly. Okay? I mean, it's not difficult. It's just tiresome. Lots of small calculations. Look at my lecture notes and you will see and you will understand why I don't want to do it here. Okay? But it's possible to do it and you get the right answer. Instead, I'm going to do something else. I got inspiration from it. I should focus on double panels. How does it look like? Well, actually, there is a choice how to label it. And if you don't want to get into big trouble, if you want life to be nice, you are going to label it like that. C will be the central point, and you go to the right and to the left by h. And you have your function, and you have 3 pieces of data, and you ask yourself, I'm interested in this area. So we want this. Integral from c minus h to c plus h, fx dx. Now, a little problem. Previously, we developed expansion for the panel between c and c plus h. We could develop a new expansion for this integral, but it's too much work. Instead, I'm going to do a little trick and recycle the results that we had before. Mathematicians were actually the original recyclers. We are really kings of recycling. So I'm going to split it into 2 integrals. One goes from c minus h to c. And this is really boring. I have to keep writing this stuff inside. Okay. And now I'm going to flip these 2 limits, but we have to pay for it by attaching minus sign in front of the integral. Minus integral c to c minus h of the boring stuff, plus integral c plus h, and so on. And now, here is the trick part. This guy is just fh, and this guy is f minus h. Now for fh, we had a nice expansion. How did it go? It was like a Taylor polynomial, but we increased, okay, let me write it down. fch plus 1/2 f derivative ch squared. So the derivative is lower by 1 than expected. That's how it was. Plus 1/3 factorial f double prime ch cubed, and so on. And I will actually have to carry it for longer, unfortunately. Anyway, what we are doing now, we are subtracting. And here, we are putting the same formula, but instead of h, we are substituting minus h. So it will be minus fch, because there is no power. Here is a square power, so the minus disappears. It gets swallowed up. Here is a cubic power, so it takes minus h and spits out the minus. Here we go. And then there will be plus, because there is 4th power, and 4th power follows, and so on. So, when all is said and done, and when the dust settles, what do we see? Minus minus is plus. 2fch. Minus plus is minus. This one goes away. Minus minus is plus, they add up. Twice 1 over 3 factorial f double prime c h cubed. The fourth power cancels. The fifth power stays and it appears twice. Fourth derivative, h to the power 5. Sixth power disappears, and the next one to appear will be the seventh power. So that's the expansion for this double panel integral that will be my target. This I want to achieve using my data. And I will need a lot of room for it. So I'm going to erase this part and copy the outcome on the top. And then we will get to it. Okay, so what's the pieces of data that we have? We have f, c minus h, we have fc, we have f, c plus h. fc is just fc. For f, c plus h, we had an expansion. fc plus f prime ch plus 1 over 2, okay, f double prime ch square plus 1 over 3 factorial f triple prime ch cubed plus 1 over 4 factorial f the fourth derivative c h to power 4 plus 1 over 5 factorial f fifth derivative c h5. Actually, I should have written f and Roman 5, but I actually like those fancies. I really enjoy writing them, so I will forgive myself for doing that. Okay, sixth derivative, f1, 2, 3, 4, 5, 6, and OH7. Wow, that's beastly. Perhaps I should have stopped one term earlier. Yeah, I think I could. Okay, I will make it up here, because fc minus h is the same expansion, just for h I'm putting minus h. So it will be fc, here minus, f prime ch, here plus 1/2 f double prime ch square, minus 1 over 3 factorial, and so on. Now, plus 1 over 4 factorial. I'm actually beginning to go in automatic mode, which is not exactly okay, because then you make mistakes. I should wake up my brain. Yeah, I give up. Okay. Wow. Okay. Now we can see that there's imbalance between the number of derivatives and the number of h's in these lines. So again, we have a motivation. We want to take these three lines, these three rows, and multiply each of them by h. Definitely. And then those terms start looking similar. For instance, there will be second derivative, h cube. See, it fits nicely. Okay, here we go. The next step, again similar to the previous trick. I'm going to use linear combination of these pieces of data and try to match this linear combination as best as possible to this part. So this one gets multiplied by A, this one by B, this one by C, and then I sum it up. And I get A times H fc minus H plus B times H fc plus C times H fc plus H is equal to, let's go for it. Okay, everything is multiplied by H, factor it out. Fc, factor out, what's left? From here A, from here B, from here C. Okay, this one is multiplied by A, this one by C, then they are summed up, and also multiplication by H. So you can factor out the derivative, you can factor out H squared, and what is left is C minus A. The next one, it's similar. I increase the power of H, factor out 1/2, and this time I'm summing up. So it's 1/2 A plus C, second derivative times H cubed. Okay. Here I'm subtracting, factoring out 1 over 3 factorial, subtracting, so it will be c minus a, the third derivative, h to the power 4. Here I'm adding, factoring out 1 over 4 factorial, a plus c, the fourth derivative, h to the power 5. Here I'm subtracting 1 over 5 factorial, c minus a, the fifth derivative, h to the power 6. Yeah. Because I'm increasing the power by 6. Yeah. Plus OH7. Because this tail actually is OH6. This one is OH6. I put them together and I raise the power by 1. Okay, that should be it. So this is the term that I'm looking for, linear combination of data. This is the term that I'm trying to achieve. Let's achieve it. Okay, here in front of this expression is 2. Here in front of this expression, I want to see 2. The first equation reads, where will it read? Here. A plus B plus C is equal to 2. Okay. H square is missing here, but not here. So this term must be 0. C minus A must be 0. Okay, the next term is the cubic one. I want 2 over 3 factorial, which is 1/3, by the way. So I want this baby to be 1/3. Therefore, the equation reads A plus C is equal to 2/3. Okay. And that's it, because I have 3 parameters and 3 unknowns. So I can make no more assumptions or no more requirements. And then the remaining tail over here and the remaining tail over here, they will create the error. Okay, so there I will have to resign myself to the fate. We will see what comes out of it. Okay, let's see. Over here, from the second equation, A must be the same as C, obviously. And therefore, from these two, I get that A is the same as C, and it's 1 over 3. So far, so good. If A plus C is 2/3, I can put it into the first equation and subtract, and B becomes 2 minus 2/3, which should be 4 over 3. Voila. So that determines how I'm going to approximate a new panel. Good. Now, let's determine the error of the new method, and let's write down what the method actually does. And for that, I will need room. Okay, so let's have a look what's happening with one panel, or rather double panel. C minus H, C, C plus H, our function, 3 pieces of data. Okay, the area is supposed to be approximated by an expression like that, where A and C are now 1/3, and B is 4 over 3. So, if I factor out 1/3 to make my life easier, and if I factor out H out of these guys, then the formula reads F C minus H plus 4 times FC plus F C plus H. And that will be the key for our final work. But before we get there, let me rewrite it once more. I am going to write 2H there, and you will see why in a second. And therefore, there will be 1 over 6 here. So let me start with 2H, division by 6. And here we have FC minus H plus 4 times FC plus FC plus H. That's a different form, which is not really practical, but it offers a very interesting interpretation. This product here suggests that I can look at it as an area of a rectangle. This rectangle has base 2H, which by a remarkable coincidence is exactly the width of this double panel. So here I can see 2h. And therefore, this expression on the right represents height. So I'm choosing height in this rectangle, and I'm taking into account values of function at all 3 points, but not equally. Notice that if I multiply out, it will be 1 over 6, 4 over 6, 1 over 6. These coefficients sum up to 1. This is so-called weighted average. Okay? And weighted average is just like an average, but it means that some of these pieces of information are more interesting or more important than others. And I can see over here that the middle point is 4 times more important compared to the guys on the outside. Or if I lump them together, then they have weight 2. So the endpoints have half the weight of the middle point when the average height, so to speak, is determined. So that's the idea behind this new method. But now let's put it together. We have many, many double panels. But in fact, we also have those basic panels. There is this number n, partition size which is even, and then we split this situation into double panels. How many double panels? The answer is actually n divided by 2. This will be handy very soon. For each double panel, I'm going to use this approximation, and I sum them up. So the integral gets approximated by, from the first double panel, there will be 1/3 h, and there will be the first value, f, which is actually this point on the left, which is fx naught. Then 4 times the point in the middle, which is x1, and the point at the right endpoint of this double panel, which is fx2. Then I add another area for double panel, which comes after that. This is x2, x3, x4. So I'm taking the one on the left just once, fx2, the next one 4 times, and the next one just once. x4, yeah, x4. And I keep going. What happens? That's interesting. The guy on the left is taken just once. Poor guy. The next guy is taken 4 times because it's the middle of a double panel. A very important guy. The next guy is on the edge of a double panel, but it's actually shared by 2 double panels, so it's taken twice. So it's like medium importance. The next guy is in the middle of a double panel. It gets taken 4 times. The next guy is shared. It's taken twice. You can see the pattern. 4, 2, 4, 2, 4, 2, and so on. And you keep going until you reach the second last guy, which is in the middle of a double panel. So it's 4 times. And the last guy is taken just once. That's the new method. This is called the Simpson method. Here we go. I would be very surprised if we see something else. Yeah, Simpson rule. This is called by somebody called Simpson. It was a guy who was actually employed to estimate the volume of ships based on some measurements for the British Admiralty. So this was actually a very practical method. Does the pattern agree with ours? Yeah. 1, 4, 2, 4, 2, 4, 2, 4, 2, and 1. And there is some attempt to write it down using summation notation, which is, I mean, it's perhaps a little bit more compact, but it's less transparent. So I'm not sure it's actually any progress there. Okay, the Simpson method. How good is it? We confidently expect this method to be of order 3. Let's have a look at local error. What is the local error? Well, the local error is definitely going to be this series, and from that we subtract this series. Definitely. So, 2 here, cancels. Good news. 0 here, cancels. Good news. 1/3 here, 1/3 here, cancels. Good news. The next term will create the error. 0 here, c minus a here, which happens to be 0. This is a big piece of luck. Normally, this h to power 4 would be the local error, but because the situation is symmetric, this power disappeared in our target formula, but it also disappears in this linear combination because A and C are the same numbers, they are equal. So actually, or even powers in this expression will be 0 automatically. Amazing. So what is the first non-zero number? Well, we don't really know yet, but the good candidate for the first non-zero number is this one, the 5th power. We have to work out whether perhaps this number and this number are different or not. We don't know, we have to calculate. So the local error is, let's see, I'm going to factor out the 4th derivative and the 5th power, and then there will be something left in the bracket. And in the bracket there will be 2 divided by 5 factorial minus 1 over 4 factorial, and A plus C happens to be 2/3. Times the 4th derivative, h to power 5. And now the trick is that the 6th power disappears and the error is OH7. This will play some role later on, that in the error also the 6th power is missing. But right now we don't really care. We could have written OH to power 6 and it would have worked perfectly. Okay, so no problem there. I just don't want to lose information if I already have it. Okay, how much is this one? Okay. Let me think. Okay, little thinking corner here. So the common denominator should be 5 factorial definitely, because here I cannot create 5 in any way, and 3, extra 3. Now to get this, I would have to put 6 over here, and 10 over here. Okay, I need larger thinking corner. 6 minus 10 is -4 usually, over 3 times 5 factorial, which is, okay, 4 cancels, 2, 3, 5, 2, 3, 5, 10, 90, 1 over 90, 4 over 90, 1 over 90. Is that right? Yeah, 1 over 90. So the local error is -1 over 90, the 4th derivative times h to power 5 plus OH to power 7. Okay, let's see the global error. Now the global error can be estimated by, and now it gets interesting, we have to be careful. We have to sum up local errors for every double panel. How many double panels are there? The answer is n over 2. That's a change. Before we were putting it n times. Now we put it n over 2 times. So we take n over 2 and we put upper estimate for the local error, which is 1 over 90 times the maximum of the 4th derivative times h to power 5. Let's ignore the O part. We will ignore it anyway. Okay. Now we substitute for n. N creates b minus a. So it's 1 over 180. B minus a. Then there will be m4. And 1 power of h cancels. So the conclusion is that the global error is OH to power 4, which is better than we expected. This is a bonus for the symmetry of the situation. And by the way, if you decided to try triple panels and a cubic polynomial, then there is no bonus, and you would really get OH to power 4 as expected. Okay? So this method actually has the same quality as approximation by cubic polynomials over triple panels, but less work, which is wonderful. So this method is actually very useful. It's one of those default methods. If you want numerical integration, this is a good candidate. Okay, we just found an estimate. Let's confirm it officially and then ask what does it mean for us. Okay, so we can see, let's go right away to the end. 1 over 180. Okay, I got lucky. I don't always get it right. Sometimes I make a small mistake and then I have to do it again. So yeah, I am feeling really great now. M4, B minus A, H to power 4. Yeah, everything fits. So I got it right. Wonderful. Okay. I didn't do an example by hand because I'm not going to ask for Simpson method on a test by hand. I don't think there is much point in it. Computer can do it better and faster, whatever. So I guess I can save this room for a little story. Okay, we have step size. We decide to divide it by some integer, positive integer a. The original error gets divided by, and now let's just imagine that here instead of h to power 4, we put h over a, that all to power 4. So 1 over a to power 4 gets factored. And that's the real beauty, that's the real strength of the order of a method. It's not that trapezoid for the same n gives you a better answer. This could be an accident. And sometimes it's actually the other way around. Sometimes a worse method can give you for a specific step better answer because it likes the problem. This can happen, okay? Fatal attraction. But the real heart is at the improvement. Here, when you double the step size, double the partition size, the error gets halved. Here, it got divided by 4. For Simpson, it gets divided by 2 to power 4, which is 16. This is wonderful. Okay, let's try it out. Okay, here we go, Maple. First of all, let's go back over here. Simpson. Number of steps 4, output error. Here we go. So the Simpson rule, wow, that's also nice. 0.0013, I like that. Okay, did I miss a 0? Yes, I did. There should be 3 zeros after the decimal dot. Yeah, now it fits. It's a little bit more. I'll have to take this into account. Okay, let's make prediction. This is the error for partition size 4. If I double the partition size, this gets divided by 16. So it will be 0.00000 130 divided by 16, 7 is not enough, 8 is almost there. 8. It will be a little bit more, but not by much. So that's my prediction. 1, 2, 3, 4, 5 zeros and 8. Now I am really apprehensive. Okay. Yeah, it's there. Okay. 5 zeros and 8. Good prediction, it works really well. So that's Simpson, wonderful. And as you can see from the chart, the error for Simpson with the same starting data, 4 or 8 partition size, gives much better answer. For essentially the same work, because the only thing which changes is this 1/3 over here. For rectangular rule, there was nothing. For trapezoid, it was 1/2. So there is tiny change. And slightly different set of coefficients. That's the only change in the formula. And you get much better approximation. Let's have a look at this trick with ratios, okay? So when I use Simpson rule as the method here, and again, 3 partition sizes, 4, 8, 16, and we will compare the errors. And we expect to see 16 as the ratios. And we do. Notice that the second ratio is closer to 16, because the smaller the step size, the better all these things work, okay? For larger step sizes, they work just like approximately, but for smaller step sizes, much better. Okay, I didn't try this picture for the Simpson method. You know why? Because we couldn't tell any difference. I commented on this before. This is just like a curving something which could be h to power 17 for all we know. So instead, I'm going to show a different picture, this one, which is a comparison of the trapezoid error and Simpson error. And when you look at it, the trapezoid error in blue is much larger than the Simpson error in red. This doesn't prove anything, but it's a strong suggestion that the Simpson method really has a much, much smaller error. You can see that it sort of hugs the h-axis, which is a significant hint that the power that we see here for the red curve is higher than the power for the blue curve. Okay?